Hello and welcome back everyone to the YOLO series. And in this video, we will look at the basic terminologies used in YOLO literature. And in this video, we're going to start off with activation functions. So basically, the contents of the basic terminologies section includes activation functions, and second, we will take a look at the structure of YOLO, which includes the backbone, neck, and head. On the third section, we will talk about matrix like IOU and non-maximum suppression. And finally, we will finalize this section by discussing about the mean average precision. So you might have heard about activation functions if you have taken any course in deep learning, but specifically for YOLO, we use two types of activation functions. And in order to understand how they work, we need to understand some concepts about activation functions. So the major purpose of any kind of activation function in neural networks is to introduce a nonlinearity between the input and the output. So what does that mean? So as you might have noticed in deep learning courses, if there is an input and you put it inside of a function and you don't put any kind of activation functions, the next layer, which is going to receive the input from the preceding layer, is going to have a linear relationship with that layer. So we don't want that kind of linear kind of relationship. So that's why we use activation functions. So they basically decide when to fire a neuron or activate a neuron and when not to activate a neuron. So if we do not use activation functions, so there will be a linear relationship between the input and the output variables. And the network will not be able to solve complex problems because of this linear relationship and its limitations. So the main objective of introducing an activation function is to introduce nonlinearity, which should be able to solve complex problems in natural language processing, classification, recognition, detection, and also segmentation. So once we understand what activation functions are, let's start by looking at the first activation function, ReLU. And we will cover ReLU because it's connected to Leaky ReLU, which we're going to look at in the next section. And the reason that we are looking at ReLU is because Leaky ReLU depends on this activation function. So ReLU is an acronym, and it's the short form of Rectified Linear Unit Activation Function. And it's defined in a piecewise defined function as the maximum of the input and 0 is going to be assigned to the function output for any values greater than 0. And it's going to remain 0 for values which are going to be less than 0. So as you can see from the picture, you can see that we have for negative values, we have the output as 0, and for values greater than 0, it's going to have a linear relationship, and this basically have some kind of advantages, and we're going to discuss them now. And some of the advantages of using the ReLU activation function is faster learning. So we can observe that when x is greater than 0, ReLU has a constant gradient. So in your math class, you might have discussed about gradients and computing gradients from graphs. So when you compute the derivative and the second derivative of a function, so if it has a constant slope, so it's basically going to keep increasing or decreasing. So what's the benefit of not having a constant gradient? Because we want the gradient to be constant so that the chances of there are no chances for vanishing gradients to occur at any point in time. And vanishing gradient is a case in neural networks where the gradients decrease and vanish over time as we propagate through the network. And this property also results in faster learning. So having a constant gradient helps the network to learn much faster. And the second advantage of the ReLU activation function is that it reduces overfitting. And overfitting is a case in deep neural network literature where a network learns the task that it's intended for very well, and it does not generalize to any other task. So, for example, let's say we have a classification problem, and if our network overfits, or if the function of our deep neural network is overfitting our data, that means it's learning really well for the training data, but it's going to perform very poorly when it encounters data that it hasn't seen before. So the advantage of using ReLU activation function is it has some kind of regularization effect. So that regularization is going to remove some of the overfitting. It's not that impactful, but it's necessary. So for all values of x less than or equal to 0, we know that the gradient of the ReLU activation function will be 0. And hence, less number of neurons will be fired, which will reduce overfitting and is also cost efficient. So when the activation function's output is 0, which means that neuron is not going to fire, and that means it's going to deactivate some of the neurons inside of the network, which will reduce the complexity of the network, and as a result, will reduce the overfitting. So the opposite of overfitting is underfitting. So generally, it means that the network is not going to is not even learning its input data really well. So the third advantage of the ReLU activation function is better convergence. And better convergence means that the ReLU activation function is going to, in terms of computation, it's very similar to other activation functions such as tanh, and that computational similarity is going to lead to better convergence. So sometimes you might see our network is not going to converge in a small amount of time. So if we want our model to converge to its minimum point, or when you learn in deep learning, you might have learned about gradient descent. And when using gradient descent, we're trying to find the local minimum of our function. So we're trying to learn the convergence of, we're trying to find that minimum point faster. So computationally, it's going to save us, the ReLU activation function is going to save us a lot of time. So ReLU has a lot of advantages, but it also comes with its own drawbacks. So the main disadvantage of ReLU is the dying ReLU problem. So what does it mean, dying ReLU? So dying ReLU refers to a problem when training neural networks with ReLU function, the unit dies when it only outputs 0 for any given input. So as we have seen, for values less than or equal to 0, the ReLU activation function is going to output 0. So for any type of negative input, the activation function for that particular neuron is going to give us an output of 0. So when this type of problem occurs redundantly in our model, our output is going to be stuck on the negative side, and it's only going to output 0. So our model is not learning anything new. So when training our model by using the stochastic gradient descent algorithm, the unit is not likely to return to life. It's not going to come back to life again and give you a different output. And it will no longer be useful during training. So in order to solve the dying ReLU problem, the Leaky ReLU activation function was used. The Leaky ReLU is a type of activation function that is intended to solve specifically the dying ReLU problem. And the Leaky ReLU is deployed in the YOLO v1 and YOLO v3. And a traditional rectified linear unit ReLU function returns 0 for all values less than 0. And the dying ReLU problem refers to when the unit gets stuck this way, also always returning 0 for any kind of input. So the Leaky ReLU tries to address this problem by returning a small negative value, small negative non-zero value, instead of 0. So mathematically, we can express it by using a piecewise defined function in which the output is going to be the same as the ReLU for values greater than 0. So it's going to return as the maximum of the input and 0. And when the input values are less than or equal to 0, instead of giving us a 0 value, we're going to multiply a constant called alpha with the input value, and alpha is typically a small value like 0.0001, and this constant is going to make the output very small in the negative side. So another activation function that we're going to look at is called the Swish activation function. And I decided to include the Swish activation function into the video is because the next activation function that we are going to look at, the Mish activation function, which was deployed in the later versions of YOLO, is dependent upon the Swish activation function. And this activation function was discovered by the people of Google Brain in 2017. And it's basically a gated version of a sigmoid activation function. And as you can remember, the sigmoid activation function is a very simple activation function which was used initially during the inception of deep neural networks. And the formula for the Swish activation function is we're going to use the sigmoid activation function, and we're going to apply it on the input x, and we're going to multiply that x by a constant parameter, just like the alpha we used in the Leaky ReLU. And we can also make it a trainable parameter, which is going to be a non-fixed value, and it's going to be optimized as we train our model. And we're going to multiply the output from the sigmoid activation function by the input again, and we have the Swish activation output, which is given as f of x. So as you can see from the graph, for values less than 0, the Swish activation function doesn't necessarily stay at 0 on the negative side, so that kind of mitigates the dying ReLU problem. So we have very small negative values, and it's also bounded from the negative side, which means we have a lower bound for our function, and it's not bounded above on the positive side. So when beta has a value of 0, the Swish activation function actually acts more like a scaled linear function, because as we can see from the previous slide, we multiply the input by the sigmoid activation output. So when beta is equal to 0, the sigmoid activation function is going to output some constant value, and it's going to be multiplied by the input value again, and it's basically going to act as a scaled version of a linear function. And when beta tends to infinity, Swish behaves more like a ReLU function. And so the simple nature of Swish and its resemblance with ReLU has made it popular, and it has been replaced by ReLU in many neural networks. And like ReLU, Swish is unbounded above and bounded below, as I have mentioned before. And Swish is smooth and non-monotonic. In fact, the non-monotonicity property of Swish makes it different from most common activation functions. So let's take a look at the advantages of the Swish activation function. Number one is that it has higher accuracy. So in very deep neural networks, Swish achieves higher test accuracy than ReLU. So if you use Swish activation function in your neural network instead of ReLU, you're guaranteed to have higher accuracy. And it also outperforms ReLU for every batch size. So if we use different number of batch sizes during your training procedure, the Swish will always outperform ReLU. And one property that I mentioned in the previous slide was the non-monotonicity property of the Swish activation function. So for all values of x less than 0, the Swish activation function is neither decreasing nor increasing function. So for negative values, it's not going to increase or decrease. So that's called non-monotonic. So as we can see from this figure, on the negative side, we can see that it's not necessarily increasing or decreasing. So that property is known as non-monotonic. So our final activation function, and the most recent one, is the Mish activation function. And it's given by the formula. We apply the soft plus function on the input, and we also apply a tanh function on the output from the soft plus function, and we multiply the output of the tanh function with the input again and assign it to the function f of x. So you might ask yourself what soft plus function is. It's just another function that can be expressed as the natural logarithm of 1 plus e raised to the power of x. And it's just a fancier name of this mathematical function, and you do not need to be concerned about this one. And the Mish activation function was used in the YOLO V4 paper. So most of the experiments suggest that the Mish works better than ReLU, Sigmoid, and even Swish. So like both Swish and ReLU, Mish is bounded below, and we have seen that the Swish activation function is bounded below, and it is also unbounded above, so it goes up to infinity. And the lower bound starts from negative 0.31, and it goes on to infinity. So then the value of x that outputs the value of negative 0.31 might be in between 0 and -2, as we can see from the figure. And that's all you need to know about the Mish activation function. And finally, let's take a look at the advantages of this activation function. So the first one is that the Mish activation function avoids saturation. So being unbounded above is a desirable property for any activation function, since it avoids saturation, which generally causes training to drastically slow down due to near zero gradients. So when a function is not bounded from above, it avoids the saturation during training, and saturation causes the slowdown of the learning procedure when you train a neural network, because the gradients will be very close to zero. And when the gradients are very close to zero, it means that our network will be saturated. When you have near zero gradients from the negative side or the positive side, you will be updating the weights by very small values. So in order for our network to learn, you basically want higher updates, a large amount of updates to your network. And when you have very low gradients, they're not going to modify the weights of the model by that much, so the training procedure will slow down. And the second one is that it reduces overfitting. We have already discussed it in ReLU. And being bounded below is also advantageous because it also adds that regularization effect by canceling out some of the neurons and adding a regularization effect so that it can reduce the overfitting problem. And finally, it's continuously differentiable. And ReLU is not a continuously differentiable function, which means at some point the ReLU is going to be zero and it's not going to be differentiable again. And this may cause some problems in gradient-based optimization, which is not the case for Mish, because Mish is continuously differentiable, which means we're going to get a value when we differentiate the function. So this is all about activation functions, and we're going to be looking at the Mish and the Leaky ReLU, which has been used in the YOLO literature. And thank you for joining this session.